Alright, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and good afternoon, everyone. Alright, yeah, maybe I will start straight with the recording. Uh, alright, so today we're going to be looking at, should I say this is going to be the final tutorial? Uh, we still have one more tutorial, but we're not going to like really discuss it for the dynamic. I think the dynamic we still have to discuss. Yeah, this would be the second last, I guess. Okay. All right. So today we're going to be looking at another tutorial, graph algorithm tutorial. So this week we look at three more graph algorithm, which is the Dijkstra, Bellman-Ford, and Floyd-Warshall graph algorithm. Okay. So last week we looked at part one of graph algorithm, whereby we look at BFS, DFS, topological, and MST. And as you know that algorithm programming approach, okay, to do the how do you call that, to approach to um, solve problem. Between what we looked at last week is that last week we don't look into the negative edge. So this week, all the algorithm that we looked at this week can handle negative edge. Except for Dijkstra, you can still basically compute if you have the negative edge. It's just that the solution is not going to be complete. Okay, you're not going to have a complete solution. Because somehow you might be missing the way you choose the edge. You might be missing the shortest, basically the negative edge. Okay, that's why we looked into Bellman-Ford, whereby that algorithm, that graph algorithm, can take care of negative edge, provided you do not have negative cycle inside the graph. Okay, so if you remember the negative cycle, meaning if, like, let's say the graph have a cycle, if you add all the edges in the cycle, if it is negative, meaning your graph will have a negative cycle. So in a sense, when you apply the Bellman-Ford algorithm, you can check whether you have that negative cycle by, as you know that the iteration that you have to run the relaxation in Bellman-Ford is V minus 1. So in a sense, you can run an additional one loop to see whether if there is any vertex that is still updating, okay, the shortest distance. So if there's still updating going on, it shows that there's a negative cycle inside the graph. All right, and then we looked at Floyd-Warshall, and for Floyd-Warshall, so for Dijkstra and Bellman, both of them are single source uh, uh, single source graph algorithm for all pairs. Okay, graph algorithm for all pairs. So basically, you can find the shortest path from any pairs of vertices inside the graph. Okay, so let's look at the first question. So here we have this graph, and we are going to apply the Dijkstra to determine the shortest path from vertex 1 to all other vertices. Okay, and if you see here, we don't really use this table, okay, in our lecture, but basically you can actually keep track of the distance from vertex 1 and the vertex 1 and the predecessor from the vertex while actually looking at the graph. Okay, so And basically here, you need to show what are the order of the process vertices as well. So anybody can give me the answer. Maybe we give me the answer of the order of process vertices first. And maybe later, maybe I will show you like step by step on how you can fill up this table. Or maybe some of you have already got the answer that you can provide me with the answer. It's fine as well. So can I have anyone share me the answer for question number 1? Do you remember, right? Dijkstra, the relaxation of edges. All right. Class. He knows how to use this table. It's just a matter of keeping track, just like remember in class what we was on the side picture, okay? But happen in the table, okay? Okay. So do you know how to get all this answer, class? Anybody got a different answer than this? Yeah. I think I will just show you once how do we get this table, okay? Because I don't really use this table. I always forgot to actually use this table when I do the Dijkstra, and it's always during tutorial that I realized that we have this table to do when we were in when we were doing our tutorial. Okay, so anybody first let me ask, is there anybody else who does not get this answer? At least for the order of process vertices, you should be you should be able to get this. Okay, so if you remember, we did use some kind of array or some kind of table inside the lecture where we sort of like keep track of the processed vertices, right? So the order would be whatever the order of process vertices that we can get from the table. Okay. All right. So maybe perhaps I will go through with you this table. Do I need to go through with you this table? I think maybe I should because it's a very quick one. So I think I will share my iPad. Right. So I think I better erase this first. All right. Okay. Excuse me. All right. So basically, this is what we have. And if you remember what the Dijkstra, we will have a starting point. So in this case, the starting point will be node 1. And we can update the distance to 0 and the rest is infinity since we have no idea what is the distance, right? So basically, this is what we have here right now. Okay, the distances when you initialize, and we are not sure what is the predecessor vertex, right? So we are not sure of what are the previous vertex that it is coming in. The reason why we want to keep track of the predecessor vertex is so that we can find what is the shortest path, what is the vertex before uh, uh, the destination. Okay, so let's try and do this, right? So basically for this one, the Dijkstra, we're going to start with 1, and we're going to we see that 1 is connected to 2 and 4, and therefore we can relax these edges. So node number 2, we can say that the distance is 2, and this one is 3, and we can update 2 instead of 2, it become, sorry, it is 2, and this one becomes 3. And we can also update what is the predecessor vertex as 1, right? And then how should we go about after this? We are supposed to choose which vertex to process, right? So we need to consider either this vertex, which has value 3, this vertex value 2, this, and this. So we have to choose the smallest one. Therefore, we're going to choose 2, right? So the next vertex that we're going to process is 2. So we're going to write here 2, and we're going to do the same thing again. Okay, so we know that for 2 is connected to 5 and 3. So we can relax these edges. So 2 plus 3 is smaller than infinity. Right? 2 plus 5 is 8, smaller than infinity. We can update this. So we can update this to 5. We can update this to 8. The predecessor vertex is 2, right? For both of these, right? And then we are going to again look at which vertex to process. Okay, so we have this, and this to consider, and we need to find the smallest, and therefore we are going to process 4, right? So we're going to process 4. Um, so 4 can have only one edge, which is going to 3. So 3 plus 1 is 4, which is smaller than 8. We are going to update this into 4. Okay, so we're going to update node 3. This one becomes 4, and this one we're going to update the predecessor vertex to be 4, right? Okay, again we're going to look at this thing, which vertex to consider next. We are going to consider vertex 3, node number 3. Okay, 3 can only go to 6, and we're going to update this one. 4 plus 2 is 6, is smaller than infinity. So we are also going to update here, and we're going to say that this comes from 3, right? Goes to 3. And forgot to write what is the node that we process next. Okay, and then again we do the same thing again. We're going to choose 5, right? Because it is the smallest at the moment. So we're going to process vertex 5. So vertex 5 only have one edge, which is 5 to 6. So 5 plus 4 is 9. It is actually bigger. 5 plus 4 is 9. It is bigger than 6. So we're not going to do anything. So we're just going to leave it. And finally, we're going to process vertex 6. Okay. So the last one to be processed is 6. Okay. So therefore, we get this table, right? Okay. So through this table,
Doctor, I think you're muted.
sorry, I just muted, is it?
Yeah.
Okay, thank you. Uh, I, that thing is muted on its own. Okay, all right. So, All right, so once we have this table, right, you can actually trace the path. Okay, so like, let's say, for example, you want to know what is the, the distance to go to 6 from 1 is 6, right? And how do you know which path to take? Is that you look at 6 and then you look at what is the predecessor vertex. Okay, so in this case, the predecessor vertex is 3. So we're going to look at 3. So 3, we look, so basically, you can say that this one, the predecessor vertex is 3. And then you look at 3 and you look at the predecessor vertex is 4. You look at 3, predecessor vertex is 4. So you can trace back. And you look at 4 and you look at the predecessor vertex is 1. So therefore, you know, this would be the shortest path to get to 6. Okay, so that is why you keep track of what are the predecessor vertex. All right. Any questions so far regarding this one? Should be okay, right? Right? No problem. All right. Okay, so let's go back to here. All right. So let's look at this question, number 2, still applying Dijkstra. And this time we need to find out what is the distance to get from the post office to house mark H4. Okay, so these are all the houses. So in kilometers. So this graph represents those houses and the distance from each other. And you want to find out what is the distance that the postman have to travel if he wants to deliver to H4. Okay, so can someone give me the answer for this one? You can actually give me like the table in the previous question, as well as the order of the process vertices, and then the shortest distance to get this to H4. Okay. All right. So what is the total distance that the postman have to travel to H4? You actually can get the answer from the table that you gave. It's just that I was looking at the table that you gave. Yeah, it's supposed to be 21. It's just that the table, this table that you give, right? This table that you give, supposedly this column is P1, P2, P3 will indicate the sequence of houses that you process. It's supposed to be either H1, H2, H3, and so on and so forth. Because you are using the approach that we discussed in class, right? Or is it something else? Because I couldn't because I'm not sure what do you mean by this P1, P2 up until P7. Yeah, it's supposed to be H. So basically H4. So H4, you see here, the distance is 21. Okay, so supposedly it's H1. So these are the sequence, the order of uh, um, vertices that we process. So we have H1, H7, H6, H5, H2, H8, H3, H4, right? And then this would be the shortest distance. So basically, post office to H1 would be 4, post office to H2, house 2 is 12, house 3 is 19, house 4 is 21, house 5 is 11, house 6 is 9, house 7 is 8, and house 8 is 40 kilometers. Okay? And yeah, so basically, it's this one is not supposed to be P1 before it is supposed to be the sequence of houses that you process. Okay, to any question about this one? You can also do using the table that we did in question number 1. So you can also create this table, okay? And you should be able to get the order of vertices as well as the distance, okay? Or you can use the one that we learn in class, which is this table. It's just that for whoever that is giving me this answer, this part is supposed to be indicating which vertex that you're actually processing at that time. Okay. All right. So something like this. Okay. All right. Are you all good for this one? For Dijkstra? Right? So it's pretty clear, right? Okay. So let's look at question number 3. I saw the good coming up. So I just realized that one. Is it from the Teams? I think so. Okay. Is there an icon like that to say good from there? Or is it from the what? Because I never been on the other side of the Teams. So it is always me giving what. So yeah, maybe there is a way. Okay. All right. So for question number 3, I actually have 3 monitors to actually look at. So sometimes I was looking at the other monitor. Okay, so for question number 3, given the graph, find the shortest path from A to F using the Bellman-Ford algorithm. And then you have to provide the distance and the path. Okay, so for Bellman-Ford, as I mentioned just now, this algorithm can handle negative edge because provided there's no negative cycle in it. Okay, so in this case, you have to iterate the relaxation. So there's several iteration that you have to do, and you need to make sure that and then for this Bellman-Ford, basically, what you did was you're applying the dynamic programming approach, all combination of paths to get to each vertices. All right. So can I have someone to share me their answer for this one? class? Maybe give me what is the shortest distance and what is the shortest path. Anybody is giving me the answer? Do you have any problem with Bellman? So the steps, you need to write out all the all edges, okay, and then you have to follow the same order for every iteration when you want to do the relaxation, the edge relaxation. Nobody? I'm waiting. Shortest distance and shortest path. How many times do we need to iterate? Class? 5, right? Which is the number of vertices minus 1. Answer, quick. Still waiting for the answer. What is the shortest distance? What is this question asking? Oh, A to F. We want to find what is the F. Shortest distance to F. Shortest distance to F is 1. Anybody else got a different answer? And then what is the path? You can actually do the same way, you know, to track the path using the first method, you know, like you trace one by one. So basically you will have several columns that keep track of what are the previous how do you call that, the predecessor vertex, okay. uh, and then basically you know that all the edges have been relaxed completely when there is no update. When you run the relaxation, there's no more update. Okay, so and then therefore you know that you have complete the cycle. Okay, A D B C E F. Okay. All right. Do you know how to get the answer for this one? Who doesn't know how to get the answer for this? Is there any chat? No. Anybody writing here? No. So all of you know how to get this? Yep. So ADEF, shortest distance is? What is the shortest distance? It looks like you're supposed basically the distance should be the shortest distance should be 1, and the path is A D B C E F. So let's see how did you do this? There's nothing wrong. I really like to see different answer because, as I mentioned, I like to dissect wrong answer to see, you know, like either is it the way you understand it wrongly, or the way you calculate it, like sometimes possible as well. It's just that so basically it's a common mistake. So we want to have that as well. So let's see how to do that. Okay, AD uh 6, 7, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so you have all the edges. So for the first iteration, uh uh but then you get the distance one here. So basically I think the way you do your element, basically your relaxation is correct, because in the end you get this one, right? The distance is one. It's just that you cannot get the path because you do not keep track of the predecessor vertex. So in order for you to know what is the shortest path, you need to have this table as well. You also need to construct this table when you keep track when you do the relaxation. So basically, instead of having just one column, you need to do like this for several iteration. Okay. So yeah, I think the way you implement, you did not keep track of the path, so that's why you have you cannot get the final path here, right? So the final path to get to F with only value one is if you go through A to D, okay, that is -2, and then to B that is 0, and then go to C, which is 1, and then go to E, which is 0, and then goes back to F, which is 1. Okay, so that is the path to get from A to F with distance 1. Okay, so in this case, I don't think it is like a map of a housing area. Maybe it is something like I don't know, maybe some kind of value, or maybe direction. Let's say, for example, okay, that you represent using the graph. So in this sense, in order for you to get from point A to point F, the distance is 1 and the path is ADBCEF. Okay, so tak salah. It's just that the way you do the development is fine. It's just that you did not keep track of the path. Okay, so in order for you to keep track of the path, you need to have that table just now, like what we did in question number 1. This one. Okay. All right. Okay. So question number 4. So it's going to be a quick tutorial as well today. So question number 4, we have another Bellman for algorithm question. But in this question, you have been given the edge already. And then you have to choose either A, B, C, or D. Is the correct answer after you apply the Bellman for algorithm for the first iteration. So what is the answer for this one, class? So basically, this is what you're supposed to do if you want to check for the path. All right. For the second question, what is the answer for? What's the answer for question number 4? The answer is A. Do you want me to go through how do we get answer A, or all is good? Since we have some time, so I might as well just go very quickly how we get this answer. Is that all right? Oh, so it's one already all good. How about the rest? Can you get the answer here? Answer A? Saya pun. Okay, siapa yang tak ada? Saya bagi, I give you like 30 seconds to say you want me to go to do this, show you how do we get this one. It's the same. It's just like the first question. Anybody? So we're just gonna do this question then. Okay. All right. Let me change. Okay, then I will go through this question. Just so, because I think we do not really do this method when we do example inside the class, right? So um, okay. So okay. So let's try do this one, right? So basically, since we want to make sure that the first iteration, all of us get the same answer, the sequence of the edge has been given. Okay, these are the sequence of the edge that you need to go through one by one, right? So let's start to relax the edges based on this one. So we start from S, right? And then basically we can update. So S, the distance is 0, and the rest is infinity, right? And we can also update the distance in our table as infinity, right? And then we look at the first edge, which is SA. SA, we can relax. So SA distance is 4. We can relax this to 4. So this one becomes 4. And the predecessor is S. So the next one is SC. So SC is -4. This one is infinity. So we can update this to -4. So here we can update to -4. And the predecessor is S. The next one is edge AB. 4 plus 1 is 5. 5 is smaller than infinity. So we can update this to 5. B, so this one we can update it into 5, and the predecessor is A. The next one is BC. So BC, 5 plus 3 is 8. 8 is bigger than -4. We're not going to do anything. BD, 5 plus 8 is 30. So we're going to update this into 13. So this one becomes 13. And the predecessor is B. BE, 5 plus 5 is 10. Smaller than infinity, we're going to update this into 10. And the predecessor is B. And then we're going to look at CD. CD minus 4 plus 4 is 0. So it's smaller than 13. We can update this to 0. So 13 update it to 0. And the predecessor now is C. CA. So CA minus 4 plus 1 is -3. Smaller than 4. So we're going to update A to -3, and the predecessor would be C, right? And finally, DE. So 0 plus 12 is bigger than 10. We're not going to do anything. So that is how we get the answer A. So 0, infinity 4, -3, infinity 5A, infinity -4 S, infinity 13 0 C, BC, right? Infinity 10 and B. Okay, so assuming that for question number 3 just now, so if like let's say for the last iteration, this is what you get, you can actually trace what is the path. So let's say you want to find what is the path to get from S to E. You can look at E, and you look at the predecessor is B, and you look at B, and you look at the predecessor, and it comes from A. So basically, since this one is not complete, so once you run it until it's complete, you should be able to get this table, and then you should be able to get the path. So and then you should be able to also get how do you call that, the distance as well. Okay, it's just that in this case you have to run it for 5 times. So you have to run it again and update this table for 4 more times, and then the last table that you get should be able to get you the path as well as the final distance for the graph. Okay, so Bellman Ford is single source to single source graph, and yeah, so basically that is how you get the answer A, right? Any question regarding this tutorial? We do not have any example for the float washer, right? So did anybody manage to go until the end of the example that we have inside the class? Because I think we leave it just like right at the beginning. But did you manage to do it until the end for the example that we do in class? Class? Did you manage to finish it? You didn't try it. Did you? Because I really want to know, because the past few past few times that I actually do that, I always get a different value, like the last two matrices. So uh, I, I a few times already, so I think there's some error in the comments book. So that's why I was wondering if any of you can complete that one. Uh, um, then perhaps like I can verify that answer. No, nobody did it. So I'm going to ask the next session to actually do that for me. Okay. Um. All right. So any question about this tutorial? Okay. So the algorithm that we looked in this topic, the two parts of this graph algorithm is the fundamental ones. So we do not look into Johnson's algorithm, because that is it's good if you want to go and have a look at it, because it's a little bit tricky algorithm to apply, but it is also but it's good it is also good for you to know the algorithm as well. And basically, like once you and these are all very fundamental. You may find a very variety of graph algorithm out there, which addresses different kinds of optimization. Okay, so as you know, that graph is a very versatile data structure that you can use to represent uh, a lot of things. Okay, and basically you can also find a lot of graph algorithm out there to for the optimization as well. All right. Okay. All right. So if there's no more questions, or do you have any question, last question before for regarding the group project? No. I have posted the link to uh, to the peer evaluation. So please fill it up, okay? And please be frank. If there's an issue, please write it there, okay? Because then like it's very difficult for me to follow up if, like, let's say for example, after the Viva and then suddenly people sending me messages. So it's very difficult for me to have proof, because this would be the proof that if, like, let's say that if there's anyone or any member that have a problem, please be honest and put it there. Okay. It's going to be PNC, private and confidential. Um, and as I mentioned, please be please be honest. If there's an issue, if you think that someone do not carry their weight during the group project, please state inside there. Okay, that would be the how do you call that? No, should I say the feedback form for me to know how is the progress, how is the uh dynamics of your group, I guess. Should I say that? Or the teamwork of your group? Okay. All right. So no more question? All good? So in that case, I will end the tutorial for today. Yeah. So I'll see you next week. So next week we're going to be looking at not one final tutorial lecture. Supposedly this week we should complete our all our face-to-face lecture. Supposedly next week we are just going to have the asynchronous lecture for multi-trading. So I think we are just going to be uploading the slides and the tutorial. So I'm not so sure whether we are going to do the multi-trading tutorial as well. But next week we're going to be looking at dynamic programming, okay, for our last face-to-face lecture. Okay, so I guess that's it for today. Let me stop the recording. And I guess I'll see you next week, right? Thank you, everyone. Bye. Assalamualaikum warahmatullahi wabarakatuh. Bye.